So hello guys, today I will present segment anything paper. First of all, this paper is not published anywhere yet, so it's in arXiv right now. It's published by Meta recently. Uh, so they try to come up a foundation model for image segmentation, and they also release a large diverse dataset consisting of over 1 billion masks, and they try to answer following three questions. So what task will enable zero-shot generalization? What's the corresponding model architecture for this? And what data can power this task and model? And I will go through each one by one. So first of all, for the task. So they call it segment anything task. They aim to define a task with analogous capabilities to the next token prediction task used in natural language processing, which is used for foundation model pre-training and solving diverse downstream tasks via prompt engineering. So they propose a new task called promptable segmentation, which enables zero-shot transfer to a range of tasks via prompt engineering. But the thing is, this segmentation should be flexible and ambiguity aware. For example, if you have a point on a shirt, it might indicate either the shirt or the person wearing it. And it forms the basis for their segmenting model. And as an example, for the kind of prompts they used is points. You see this, right? Okay. Points, bounding boxes, masks, dense masks, and some texts, like cat with black ears. Then the model. So they use a existing model called masked auto-ingrading pre-trained vision transformer, but adapted to process high-resolution inputs because their dataset has a high-resolution images, and it runs once per image. And then after running it once per image, you can do as many prompts as you want for that particular image. And it has prompt encoder, as you can see here, which accepts sparse and dense prompts. The sparse prompts are points, boxes, and text. And they represent points and boxes by positioning encodings summed with learned embeddings for each prompt type. And they use freeform text with an offset text encoder from clip. And they represent the masks by embedding using convolutions and summing element-wise with the image embedding. And for a decoder, it's a simple transformer decoder block followed by a dynamic mask prediction head. It uses prompt self-attention and cross-attention in two directions, from prompt to image and from image to prompt, to update all the embeddings. And after running two blocks, they upsample the image embedding and they apply MLP to map the output token to a dynamic linear classifier, which then computes the mask foreground probability at each image location, as you can see here. How do they do training? So for training, they try to simulate interactive segmentation setup. So with equal probability, either a foreground point or bounding box is selected randomly for the target mask. And these points are sampled uniformly from the ground truth mask. First. And boxes are taken as a ground truth bounding box, but they add some random noise to a maximum of 20 pixels. And then they make a prediction from this first prompt, and then they select uniformly subsequent points from the error region between the previous mask prediction from the first prompt and the ground truth mask. So, and each new point is foreground or background, depending of the error region to be false negative or false positive, respectively. And these points are sampled 11 times iteratively per mask. As a loss function, they use a linear combination of focal loss and dice loss. And For IOU prediction head, it's trained with mean square error loss between IOU prediction and predicted masks IOU with the ground truth mask. And now resolving ambiguity. So there are some cases when, for example, this point can correspond to this who image or partial image or just the head of the bird. So for these cases, what they come up as a solution is if a ambiguous prompt is given, they predict multiple output masks. And they say it's 3 masks are sufficient per prompt. And when they backpropagate, they use the minimum loss over the masks, the minimum that occurs among these 3. And they rank the masks by predicting confidence score, means estimated IOU per mask. And now the data engine, how did they make this big data? So it consists of 3 stages. First, assisted manual. The professional annotators just label the masks by clicking foreground and background object points using a browser-based interactive segmentation tool powered by SAM, the segment enhancing model. And once sufficient data annotation is collected, this model, which was previously trained using public segmentation datasets such as COCO, was retained using only new annotated masks. And as more masks were collected, the image encoder part of this model was scaled from base to hues in terms of vision transformers. And as architectural details evolved, so in total, at this stage, SAM retrained 6 times. And at this stage, they collected 4.3 million masks from 120,000 images. The next stage, semi-automatic stage. In this stage, from the previous stage, they already have some confidence. So they make confident masks by training a bounding box detector, which is fast CNN, on all first stage masks using a generic object category. And the annotators then are asked to annotate the remaining objects. And in this stage, the SAM was retrained 5 times. An additional 5.9 million masks from 180,000 images were collected. Then they come to the final stage, the fully automatic stage. At this stage, they find out that they have enough masks with enough diversity were collected. So that's why they do the rest of it automatically. So they predict the objects by prompting their model with 32 by 32 regular grid of points. And then also they apply NMS to filter out duplicates. And they apply this model over all the images from first and second stage and also from the last stage to all images in the dataset, basically. So in the end, they have images, high resolution images, 11 million high resolution images, with the shortest side set to 1,500 pixels and 1.1 billion segmentations. And among these segmentations, 99% of the masks were generated automatically. But in the release data, they include only automatically generated masks. And they also check the mask quality. 500 images were randomly sampled, and the annotators asked to improve the quality of these automatically generated masks. They found out that 94% have greater than 90% IOU, with 97% having greater than 75% IOU. And some properties of this data set, as you can see, main thing is the number of images. You can see the SA1B has like 11 times more images than open images, the largest existing segmentation data set, and also 400 times more masks than largest existing segmentation data set. And they also show some geometric distribution of this data set, having diversity. Now they do the zero-shot transfer experiments. So First of all, they use model mask autoencoded pretend vision transformer hues trained on their own dataset that includes only automatically generated masks from the final stage of data engine. And they, as a testing, they have 23 datasets compiled with diverse image distributions as follows. For evaluating SAM's zero-shot transfer capabilities. So first, they do single point valid mask evaluation. The task is simple. We just segment an object from a single foreground point. And they compare it with existing strong interactive segmental model, RITM. And as you can see from the results, the same yields higher results on 16 out of 23 datasets by as much as around 47 IOU. Then they do edge detection, a classic low-level task on BSDS 500 dataset. One thing to note that SAM was not trained to predict edge maps or had any access to BSDS images during the training. And obviously it lags behind the state-of-the-art methods that learn biases of BSDS. As you can see from this image, the ground truth has less edges compared to the SAM. That's why it does not perform well like others. Because it fails to suppress the edges that needs to be suppressed for learning the BSDS 500 dataset. And then they do object proposals, which is a mid-level task of the proposal generation. So for that one, they use LVIS dataset because of its large number of categories, more than 1,000 classes. For that one, they simply use the masks from SAM as object proposals. And it outperforms, surprisingly, the vision transformer on medium and large objects, as well as the rare and common objects, as you can see here. This SAM single out is the ambiguity unaware version of SAM. As you can see, it's not as good as the ambiguity aware version. So it's important for SAM to be ambiguity aware. And next, they do instance segmentation, simply segmenting it on an instance level. So for that one, they simply run an object detector, in this case, vision transformer detector, and prompts SAM with its output boxes. And they evaluate on LVIS and COCO, and it underperforms compared to vision transformer detector. But according to a human study, it produces better quality masks, as you can see here. So this is ground truth, this is SAM, and this is vision transformer, and so on. Lastly, they do text to mask experiment. The task is to segment objects from free-form text. So for that one, they modify the SAM's training procedure to make it text aware while not requiring new text annotation. So for that one, they extract clip image embedding from manually collected masks with area larger than 100 square and prompt it to SAM. But at inference time, they run text through clips text encoder and they give the output embedding as a prompt to SAM. And as you can see, it fails to make correct predictions sometimes, so additional point might be needed to fix that problem. And they mention about the limitations. So first of all, it can miss fine structures and hallucinate small disconnected components at times. And it does not produce boundaries as crisply as more computational intensive methods that can zoom in. And they say dedicated interactive segmentation methods are expected to outperform SAM when many points are provided. And SAM is designed for generality, breadth of users, and high IOU interactive segmentation. And also SAM's overall performance is not real time. because they are using heavy imaging order, but it's run once per image. And they said this text-to-mask task is actually exploratory, not entirely robust, but they say it can be improved with more effort. That's all.
So I saw there's some demo for this.
Yeah.
But
Yes. And as they extract embedding for the each. Basically add box. Like this, yeah. Yeah, it's not that good when it do it. It's
that's not very derived for the semantic segmentation, but still it's
yeah.
for some
Yeah.
object.
What the bugs? Yeah.
Or maybe we had to use this tool for the big
But it's already done. It's already done.
This kind of some zero shot things are quite promising.
Yeah.
So using large models like large language model, some clip.
Yeah.
Have you read the clip paper?
Not. Yeah, he's gonna present so.
Yeah. Anyway, there's a lot of effort required for training such big model, but you can use their pre-training rate to do different things.
Yeah.
So,
Yeah.
and they are quite good for zero shot learning.
Yeah, zero shot.
Developing some idea towards this kind of zero shot thing is also very promising.
Yeah.
Or maybe for your problem, maybe we are dealing with summer and artistic vision, then for the segmentation, so maybe summer information that can give some point, that gives some, maybe we can do that kind of thing.
Yeah.
That thing.
Maybe the paper output into the best paper outcomes because they use pseudomonas or something. So some
Your paper?
Yeah.
Okay.
What is I have one question. So what is the difference between the mask that we provide to the model and the final mask that we obtain?
Mask.
We input the mask, right?
Yeah.
And we have output the mask.
We put like loose mask and output comes from the model that fine tunes that mask.
Yeah.
But our input could be some point.
Point is better actually.
Rather than mask.
Actually, for training, they did not use masks, they used points and boxes. Yeah.
And I heard that here they are providing some food.
Yeah, they provided some. I actually ran it once, but the problem is this one does not label the masks they generate, so it just gives all the masks to you.
So you mean labeling means some semantic?
Yeah, some instance level thing. They don't so that's they don't provide that. Yeah, they say they ask the annotators to label them, but they didn't collect those information. Stop it.